Okay, we're going to talk about reduction, electrophilic addition and substitution, and the nitration of benzene in this discussion. So there's a couple new mechanisms and then just some reactions where you need to be able to predict the products and state conditions. Okay, so you might remember back in Unit 3 that we learned about oxidizing primary and secondary alcohols. And we know that if we can oxidize something, then we should be able to then reduce the product. Okay, so it's just the reverse of the oxidation process we learned before. Now, in order for reduction to occur, you need a reducing agent. So there's two possible reducing agents that we might use for this: lithium aluminum hydride and sodium borohydrate. Okay, so lithium aluminum hydride is stronger. So this is the only one that can be used on carboxylic acids. Sodium borohydrate can be used for aldehydes or ketones. Now, when we represent either agent in the overall equation, we're going to write it like this: two hydrogen atoms, and we're putting the hydrogen in brackets. So for an aldehyde, the general form of the equation would look like this: R meaning a carbon chain, CHO, that's the aldehyde, the carbonyl group at the end of the carbon chain, plus 2H, and that gives me the primary alcohol. For a ketone, it would look like this: the first carbon chain, the carbonyl group, second carbon chain, plus 2 hydrogen, and that gives us RCHOH R prime. Okay, so if we reduce an aldehyde, we'll get a primary alcohol, and if we reduce a ketone, we'll get a secondary alcohol. That makes sense, right? Because we learned that primary alcohols can be oxidized to form aldehydes, then further oxidized under reflux to form carboxylic acids. We learned that that secondary alcohols can be oxidized to form ketones, but no further. All right, so let's look at a couple of examples. What conditions are necessary and what product is formed when butanoic acid is reduced? Okay, so the condition that we have to have here, we have to use lithium aluminum hydride as the reducing agent, okay? And if we were going to show the process, we would first show our butanoic acid. And I'm not going to draw on all the hydrogens just for simplicity's sake, okay? But those, of course, are all hydrogens. So in the first step, I would produce butanal. And then it could be further reduced to form butan-1-ol. Okay. So the next says, what conditions are necessary and what product is formed when propanone is reduced? Okay, so this is a ketone. So this is just going to be one step. So the conditions necessary, we can use either reducing agent, either lithium aluminum hydride or sodium borohydrate. And when propanone is reduced, I'm running out of space just a little bit here. We'll get propan-2-ol. All right, now we're going to learn the mechanism for electrophilic addition. Back in Unit 3, we already predicted the products. Actually, that was in Unit 3. We already predicted the products of these reactions, but now we're going to talk about how that occurs. All right, so let's review and talk about what an electrophile is. So remember, an electrophile is something that's attracted to electrons, so it's electron deficient. Now, in this particular scenario, the electrophile is the molecule that's being added, basically. Okay, so the molecule that's being added across the double bond is the source of the electrophile. Now remember, these addition reactions, we're adding to an alkene. So the double bond in the alkene is basically a region of high electron density. And that is what attracts the electrophile. Because the electrophile likes electrons, hence the name, electrophile. All right, so let's take a look, and we're going to look at a simple example first and then one that's a little bit more complicated. Okay, so let's look at the reaction of ethene and iodine. Okay, so let's draw our molecule. So here's our ethene, and we're going to react it with iodine. Now, the first step is that the electrophile is going to attack the pi bond. Okay, so our electrophile in this case is iodine. Now, when we show this, though, it's a little bit funny because even though the electrophile is attacking, we're still drawing the arrow from the double bond to the iodine. Okay, and that's because, remember, the arrows are not trying to show the attack necessarily, they're showing the movement of electrons. All right, so the double bonds go to one of the iodine atoms. It's symmetrical here, so it doesn't matter which one. And then we have heterolytic fission occurring with the bond between the two iodines. Okay? So we have a carbocation intermediate. And we have an iodide. And the iodide is then going to attack the carbocation intermediate. So this is a nucleophile, the iodide that's been produced, and it's going to attack, and we're going to get this as our product. So again, we already learned how to predict the product. We're just really showing what it is now, or how it happens, excuse me. Okay? So this is 1,2-diiodoethane. Now, you might or might not be wondering what happens if we have an asymmetrical alkene. Okay, so that which carbon atom is going to be the carbocation, and where is the electrophile going to add first? Okay, so let's look at But-1-ene and hydrochloric acid. All right, so first I'm going to start by drawing But-1-ene. And I'm going to draw my HCl molecule. Now, when we think about the way that the electrons are going to move here, we have to think about what the electrons are going to be attracted to. Now remember, this is a polar bond. So chlorine has a partially negative charge and hydrogen has a partially positive charge. So it makes sense the electrons are going to go towards the hydrogen. Okay, so this is my electrophilic attack step. And then there's going to be heterolytic fission. So we're going to produce a carbocation intermediate. Now, what we have to ask ourselves is, which carbon should I add the hydrogen to? Should I add it to carbon 1 or to carbon 2? Now, we have a rule called Markovnikov's rule, which is a super cool name. In an asymmetrical alkene, the hydrogen is going to attach to the carbon atom that has more hydrogens attached to it. Okay? So let's think about, so first let's draw that, and then we'll talk about why. All right, so the carbon that has more hydrogens attached is carbon 1, so it's going to get the hydrogen, and carbon 2 is going to become our carbocation. All right, and now we have a nucleophile, which is going to attack, and we're going to get our product. Now, when we're thinking about why it happens this way, we have to go back to what we learned in 10.1 about carbocation stability. So the more carbon atoms a carbon is attached to, the more stable the carbocation will be. So a tertiary carbocation would be much more stable than a primary. So here, carbon 2 is bonded to 2 other carbon atoms. Okay, so that's going to be a more stable carbocation. Okay, so the carbocation is more stable. When there are more carbons attached. Now, it's not always something that's bonded with hydrogen. You could also see something like an interhalogen, like fluorine bonded to chlorine. And in that case, again, we'd want to figure out what the more electronegative atom is. So in this case, it would be fluorine. So we would expect the chlorine to bond first, and then the fluorine to be the nucleophile in step 2. So we would expect then that the chlorine would bond to the, in the first step, to the carbon atom that has fewer carbons attached, okay? All right. Now, we're also going to talk about electrophilic substitutions. We talked about nucleophilic substitution in the last topic, and now we're going to talk about electrophilic substitution. So benzene, which you may recall from Unit 3, looks like this. There's 6 carbon atoms, and when we draw it, we draw a circle like that in the center. And what that indicates is that we have 3 double bonds, but they're delocalized. So they're basically constantly in motion. All right, so we don't have 3 localized double bonds. Now, benzene doesn't readily undergo addition. It prefers substitution. And again, that's because the electrons in the pi bonds are delocalized, so it's not easy for it to undergo the addition mechanism. Now, I'm going to give an example of electrophilic substitution with benzene. This is one of those things that's really specific. It's a very particular example. You're going to need to practice and study this. This isn't one of those things that's just going to come to you. Okay, so we're going to use the nitronium ion to do an electrophilic substitution. So the first thing that has to happen is we have to generate the nitronium ion. And you've probably never heard of nitronium before. That would make sense. We've never really talked about it. And this is a really strong electrophile. So nitronium is generated when I have nitric acid and sulfuric acid. So I'm going to draw the structures of both of those. And I'm putting charges on these, even though you know nitric acid is overall neutral. These are the formal charges. Okay, so nitrogen here has a formal charge of +1 because it has 5 valence electrons, subtract the 4 bonds. And oxygen here has a formal charge of -1 because, again, 6 valence electrons, subtract the bond, subtract the 6 lone pair electrons. Okay? So when it reacts with sulfuric acid, we see this happening. The nitric acid is protonated by the sulfuric acid, so it gains a proton. And this is pretty unstable. It's highly charged. And what's going to happen is that the lone pair electrons in this oxygen are going to be used to form a double bond with nitrogen, but then nitrogen has 5 bonds, so immediately this water molecule is basically kicked off. Okay? So then we form water and the nitronium ion. Okay? And this, again, is a strong electrophile. So you should be able to show how the nitronium ion is generated. And this process here with the arrows, that's really one step. All right, so we have our nitronium ion, which is a strong electrophile. So let's talk about how the electrophilic substitution occurs. Okay, so this ion is attracted to the benzene because the delocalized electrons in benzene are a pretty strong region of electron density. So I'm going to draw my benzene. And I have my nitronium ion. Okay, so we have electrophilic attack first, and we're going to form this intermediate. Okay, now remember that here in the benzene molecule, because there's alternating double bonds, each carbon actually has a hydrogen attached. We just don't show them when we draw it in this form. Okay, but they're there. Okay, so we get this intermediate where we've sort of disrupted the aromaticity of it because this carbon here, where the nitronium is attached, can't have a double bond. Okay? So then we have a water molecule, which will deprotonate the carbocation, and then it'll restore the aromaticity. So the water attacks the hydrogen gives those electrons back, and we get this guy here. And you can write that as plus H plus, or you can write plus H3O plus, the hydronium ion. Either way is perfectly acceptable. Okay, so this is, again, a substitution, not an addition reaction, because we still have the same aromaticity we had before. Now, once we've generated nitrobenzene, this can be reduced. So we can heat nitrobenzene under reflux with zinc and hydrochloric acid. The zinc is oxidized, the nitrobenzene is reduced, which forms something called phenylammonium. So I'm going to show this process first. And I'm just going to write it in symbols, and then I'll draw the structures. So this is the nitrobenzene that we generated through the electrophilic substitution, reacting with zinc and acid. And it forms phenylammonium. And so you've already seen the structure of nitrobenzene, but we'll go ahead and draw it again just for funsies. And then it produces this phenylammonium, which looks like this. And this is positively charged, I should add. Okay. And the nitrogen there has a formal charge of +1. Now, once we've generated the phenylammonium, we can add sodium hydroxide, which will deprotonate the ammonium and give us phenylamine, which is also commonly called aniline. All right, so I have my phenylammonium. I add my hydroxide, and I form phenylamine or aniline. Oh, and there's a formal charge there. Okay, and you're not responsible for a curly arrow mechanism here, but you should be able to write the equations for these steps. So this is a lot to remember and study, guys. So you really are going to have to focus on this electrophilic substitution and reduction section in order to do well on this on the test and the IB exam. It's a good bit of study ahead of you. Okay, now, we talked about benzene a lot, and now that we've finished talking about all the reactions we're going to talk about with benzene, it's a good time to talk about how these contributed to evidence for the structure of benzene as we know it. So initially it was proposed that benzene had alternating double bonds that were not in resonance, okay? But there's both physical and chemical evidence that contradicts that. So the first piece of physical evidence is the bond lengths. Now, if they were alternating double bonds, you would expect that we would have a short bond, a long bond, a short bond, a long bond, a short bond, a long bond. But we don't see that at all. In fact, we see that the bond lengths are equal, and they're in between what we would predict for a single bond and a double bond. So in between the predicted lengths for those. Okay? And additionally, the bond strengths are different than expected. So again, we see that the bond strengths are not as you would predict for a single and a double bond. They're in between and equal. Now, chemical evidence for the structure of benzene. The first is that it undergoes substitution instead of addition. If the electrons were localized, we would expect that it would undergo addition just like every other alkene, but in fact, it doesn't. And if you were to, like, I don't know if you remember back in Unit 3, we talked about how you could tell the difference between an alkane and an alkene because it would react with bromine water and decolorize it. That will not happen with benzene. So this undergoes electrophilic substitution instead of addition. And secondly, an interesting piece of information that was actually really key in the structure of benzene is what happens with the enthalpy changes of hydrogenation, okay? So hydrogenation is basically adding a hydrogen across a double bond, okay? Now, if this were just cyclohexatriene, so if it was alternating single and double bonds, you would expect that hydrogenation, adding a hydrogen across that double bond, would be 3 times the enthalpy of hydrogenation of cyclohexene with only 1 double bond. But it's actually much less than predicted. And that's because of resonance energy. So the molecule is stabilized by those delocalized electrons. So it actually is a much smaller energy change than predicted. Okay? So smaller energy change than predicted. And you can read about this in chapter 10 of the textbook. It's a pretty interesting read, actually. Maybe I'm biased by my love of chemistry, but it's an interesting read. So check it out at the end of section 10.1 in your textbook. Smaller energy change than expected, and that's because of something called resonance energy. Okay, so again, practice with these mechanisms. I think electrophilic addition is one you can get pretty easily, but the substitution is going to take a little bit more work, so make sure you take a look at that.